Hello and welcome to this YouTube channel, guys. I'm Abhishek Pandya, your TA, and in this particular video, I will explain about the Lab 1 of the course analog circuits. We are going to discuss everything about the questions with their solutions and their LTspice implementation. For all those who do not know what is going on, you can hang on to the video. I will explain the basic analog circuits and their implementation in LTspice with their results. So let's get started. So let's first go through the instructions of this lab, and then we will go for each question one by one. So you can see there are basic instructions given. You have already studied the diode in the lectures, right? So the components required for this lab are these components. All these components you will find out in LTspice itself. So you do not have to download anything from outside. Okay. So this is the diode which we are going to use, 1N4148. There are many other models available. I will show it in a bit. The resistors and capacitor, right? Only three components are required. So let's first start with the first question. You can see from this question that you have to design this particular circuit. Circuit is already given. Let me zoom in. This is the circuit which you have to make. Voltage source is there, resistors and diode. Okay, all this component you will find out in LTspice. What you have to essentially do is you have to find out the IV characteristic of this diode. Okay, so there is a forward and reverse bias. When you will give positive voltage here across this V1, you will get the forward bias across the diode, and vice versa. Okay, for the negative voltage, so for negative voltage you will get reverse bias. Okay, value of R1 you have to set it as 1 mega ohm, and there is one more task which is given here. Can we use lower values resistors like 1k or 10k, and what essentially it will do? Okay, the ranges of voltage for which you can do this is -10 to +10. Okay, so this is wrong. This must be -10 to +10. Okay, so that max current will be less than 10 milliampere. Okay, so this is the question. Okay, now let's just go for the LTspice solution. So this is my LTspice screen. As you can see, I have given this V1 voltage. This is resistor R1, and this is the diode 1N4148. See, if you want to know how to get this component, just press D here, you will get the diode. If you press R, you will get resistor. If you press V, you will get this V2 or the voltage source. Okay, so and wires you can just connect like this. Okay, so you can just connect like this for the wires. Like if you want to remove this, just go and remove. So this is how you just place the components. One ground is there. So that is the first question. Okay, what I am doing is I am varying this value of this DC voltage from -10 to +10 in the steps of 0.5 volts. Okay, so this is, if you right click on this, you will get this. Okay, edit simulation command. Okay, so just press right click here, you will get the edit simulation command. Okay, in there you have to go to DC sweep to vary the voltage V1 from whatever the start value is or the up to stop values. Okay, in the increment steps. Okay, so that is the syntax of how you write it. If there are multiple sources, you can use second source, third source, and so on. We have only one source, so we go to V1. Okay, so now let's simulate it. Okay, so just press this run here and you will be able to simulate. Okay, so these are the other questions, but let's just focus on here. So what is this is the plot window. Okay, so just click on the things you want to plot. Basically you want to plot IV characteristic, right? So just click here, this symbol will appear, and just click on this. What will happen? This is the characteristics which will open up. Okay, so as you can see from this diagram, that there is the current ID1. What is happening is that just click on here, you can be able to get this cursor, and you can see that you can move it here like this. Okay, so you can see current I of D1, which is the current which is flowing from the diode. For the forward bias up to this much voltage, the current is very less, right? This you can see from here, right? This characteristic from here to here. After that, it is approximately linear. Okay, it is seen to be as linear. Okay, so you can see for the negative voltages, which is 0 to -10, you will have no current. Okay, if you just move here, you will see the current in terms of nanoampere, which is approximately 0. And for the positive ones, you will have a current which is in terms of microamperes. Okay, you can see the order of this current is changed by 10 is power 3, right? So nanoampere to microampere. So that is what forward and reverse bias characteristics are. Okay, so this is the first question. Okay, you can also change the resistance value to lesser values, like as mentioned in the question. So you can just go here and you can just change this value like basically I have put it as 10k, but in the question it was mentioned to be 1 mega ohm, right? So you can just click like this, or you can just make it as 1k small values, right? Okay, so this is the other thing. You can just click here and the current will be changed by the magnitude of milli, right? So micro to milli it is changed. So you can change the values of resistors to 1k to 10k to 1 mega ohm, and you can see the variations of the current in terms of milliampere, microampere, and here nanoampere as well, for the forward and reverse bias conditions. Okay, so that was the first question. Now let's move to the second question. Okay, so let's see here, second question. This is the second question. You have to perform transient simulation from half-wave rectifier. You may have already studied this. The circuit of this is already given. This is the circuit of it. So there is a diode and there is resistor. With the help of this particular circuit, we can make half-wave rectifier. You already are familiar with the theory of half-wave rectifier in the class. So this is a frequency 60 hertz and 2 volts peak to peak. So amplitude will be 1 volt. Sine signal we will give, and we will put resistance value of R as 1 kilo ohm. Okay, and you're going to find these 3 questions. Okay, so answers of these 3 questions, that is, find out voltage waveform across the load resistor R1k. You will find out the waveform that we will get across the load resistor, which is this. Okay, here. And second is the current waveform through it, same thing. And what is the maximum voltage appear across diode. So you have to also find the potential drop across the diode. Okay, because this is not an ideal diode, it will have some voltage drop across it. Okay, that we will find out. Okay, so just let's go to the question now. This is the circuit for it. Basically, you can see what I have done is that I have put the resistance value 1k, the same diode 1N4148. Okay, you can change these diode also by clicking or right clicking on this, and this going to this peak diode, and there are so many other diodes like silicon diodes, Schottky diodes, Zener diodes. All these things we will also use. So LEDs also there, right? So all these things are there. So you can just select. You can just select one of them. What we have selected is this 1N4148. Okay, you can find the details of that as well here, right? So there are, this is a model. Okay, so this model is already available. So these are the different parameters of this diode. Okay, so you can check that out if you want. Okay, this is a known as SPICE model. So now let's just go here. So basically this is this voltage source. We can go here and sign. So you can just click on this sign. This is 1 volt amplitude and 60 hertz is the frequency. You can select OK, and we will do the transient analysis. Okay, so just right click on this, remove this first of all. Now the question is finished, so we can just remove no. Okay, so lab 1 2. Okay, now just run this. Okay, so this is the question number 1, lab 1 2. So basically, just first thing which you have to find out is the voltage here, right? So just click on this, you will get the voltage here. This is the voltage waveform that you get across the resistor. What other things were required? The current. So just go here. When this symbol changes, this icon changes, just click here, you will get the current. Okay, so this is the current. So basically voltage and current will be same. You can just right click on this, add plot plane, and you can just move this. Okay, so current and voltage will be same. Of course the units will be different, but the waveform shape will be same. Okay, now the third thing is what? The drop across the diode. Okay, just click here, don't remove this, and just look here and just, yeah. So this is the, and let's do the slide plot plane. This, sorry, just click here and just go here. Okay, so this is the waveform across the diode, the voltage waveform across the diode. This is the voltage waveform across the resistor, and this is the current waveform across the resistor. Okay, so you can see this is a half-wave rectifier. One more thing you can add, you can also add the initial waveform, this waveform. Okay, so you can just have clear idea. So this is the input waveform. This is the input waveform 0 to 1 and 0 to -1. So it is 2 volt peak to peak. Okay, this is the input voltage. this voltage is the voltage across the diode. So this Vn001 is equals to this plus this. What will happen? So this is the input voltage. Here this is the voltage across the diode. This voltage is the voltage across the resistor, and this is the current flowing through the diode. Okay, these are the waveforms. So you had to find out these particular waveforms first, currents and voltages. So you can see here, just click here, you can see this, right? So just move this. So basically this voltage, the minimum value of this voltage is what you are getting this from here. Okay, so the voltage value is approximately 898 nanovolts. So there is 0 volts. Okay, this is 0 volts. Okay, you can go from here to at peak. So at peak it is approximately 451 millivolts. Okay, so what you can find out from here is that whenever this particular voltage range crosses 0, diode starts running on. Okay, when it reaches particular value, which is approximately this, okay, which is this high value, okay, this particular value, this diode gives the voltage drop across the resistor. So for the negative cycle, when the diode is off, you will have 0 potential drop. Okay, so when the diode is off or the voltage is negative, so from 0 to negative values, this will not have any voltage across the resistor will be disconnected from the input. Okay, and that is why we are getting the 0 value here. Okay, and the same for the current, because the resistor is open circuited, there will be no current through it. Okay, so if you just click here, you can see there is nanoampere current in terms of nanoampere, and here when it turns on, after some drop across the diode, which is you can see there is a drop increase, right? This is the drop across the diode. You will get the you will start getting the waveform across the resistor and the current. Okay, now the highest current flowing from this is what it is, approximately what 450 microamperes. Okay, so same thing, 450 millivolt divided by the 1 kilo ohm resistor, that is 450 microampere current. So it is the easy calculation. Now the drop across the diode, just click on here and you can see the drop across the diode is what it rises up to approximately 548 millivolts. Okay, so that is the maximum positive voltage drop across the diode, and the maximum negative voltage drop across, basically when negative is like exactly same. So you can see the waveform of the diode follows the input for the negative values, right? From 0 to, you can see up to this much values for this range, the waveform is same as input. But when the diode turns on, some voltage drops across it, it becomes constant. The remaining waveform is applied across the resistor. So this waveform, okay, here, of course this waveform will have a lesser value than the input, which is 1 volt, 2 volt peak to peak, because there is a drop across the diode. Okay, so this is the second question. These are the 3 questions that were asked. Okay, now let's go to the third question. First remove this. Okay, remove this here from as well. No change. No. Okay, this is the third question. You can just first just go to the this third question. Okay, here you can see that this is the AC to DC converter. Okay, what we are doing is, now we are changing the what we are doing now, we are using the characteristics of this diode to make a DC signal. Okay, and we will see how we will use them with the third and fourth question. Okay, so here you can see what we are doing, we are adding one capacitor at this output. Okay, same circuit, but what we are doing is that we are just adding the capacitor. Okay, and this is known as AC to DC converter. However, rectifier is only there, only load is changed, is added. Okay, load, this only the load is changed to this R and C, parallel combination of them. Same thing, use 60 Hz supply and 2 volt peak to peak signal, and you can see, compare the difference. Basically what we have to do is that perform transient simulation of this AC to DC converter with different values of resistors mentioned in the component list. So you can, what you can change, you can use these different values, like, okay, and compare the difference if any and explain why. So you can change this value of R1 and you can see what actual changes. Okay, you can find RMS value, you can find average value as well. I will just show you in a bit how to do it. So let's just go to this circuitry, same circuitry as made as given in the PDF, and you can see, so this is 1 kilo ohm resistor, 1 microfarad capacitor, and this is the D1, and you can do the transient analysis here as well. Just click on this run, and just click here. So voltage waveform. So first of all, just select here. So this is the input. Okay. Click here. This is the output. Okay. You can just add the plot plane here, and this is the input, and this is the output. Okay. So you can see this is the approximate characteristic that we are getting. Now you can change this value of this resistor to 1 mega ohm, and you can understand what actually it is, what actually it changes. Okay, so you can just go here and click OK, and you can run it once again. Yep. See what happened, right? You can see there is a approximate constant voltage across this, right? See, it is not constant. That is the first thing. But of course, what is happening? We are seeing one range of voltages which was initially from 0 to 400, 0 to some higher value. Now they are approximately becoming constant. Okay. So initial waveform, when I had this as 1 kilo ohm, this waveform was like this, like positive waveform was coming, of course, with some 450 millivolts was coming, and the negative value was not coming. So basically this waveform, so half of this waveform was coming and the half was not coming, other half. Okay, now this waveform has changed to this. Okay, now we are getting this value. So approximately you can see this 603, 620. Okay, so 600, approximately 600 millivolt output is waveform is coming. Okay, what changed? The value of resistor change. Okay, and what it changed, that what it actually changed, it changed the value of the pulsating DC. Okay, the value which was of pulsating DC, which was of whole positive cycle, it was varying like this. Now this is only varying in the range of 20 millivolts. Initially it was varying in the range of 480 millivolts. Okay, so this is the changing in the output of this circuit. Okay, so this was the thing. Now if you just add this time, like say you can just change this transient to 1000, okay, approximately 1 millisecond. What it will change in the large frame, if you see, it is approximately constant. Okay, so that is what we have achieved. What input we had. Okay, you can just click here, and okay, so you can just click here. From this input, what we are getting is this constant, approximately constant value. Okay, so we have achieved this. Now let's get this characteristic much better. Okay, so we can just create a zoom to fit, and yeah, so this is basically the first thing. Now this is the DC characteristic that we got. Okay, so varying input changed from whole range of plus or minus 1 volt, which is this, to just a range of fluctuation voltages, which is like this. Okay, 640, 630. So basically approximately this became constant. Okay, we also have to basically calculate the value of these average values of this, right, waveform. So click on the control key on your PC and press left click. Okay, so you will get this 632 millivolts, 633 millivolts approximately. These are the average values. So average value of the signal became 632 millivolts. Okay, so this is the change in the pulsating DC to this particular constant value. Okay, so this is the one thing. Now just go, let's just go for the next question. Okay, so remove this, and so fourth question is also AC to DC converter, but here there are more questions we need to answer. Okay, and first thing is what, basically 2 volt 60 hertz signal we want to use. Resistor R is 1 mega ohm, 1000 kilo ohm, which is 1 mega ohm. This is the circuitry. Okay, this is R, this is C, this is ground, this is voltage, and this is the circuitry we are using. Okay, And we need to find out below parameters, like see the explain how this circuit works by tracing the current paths when the applied voltage is positive and when it is negative. Compare the mean value for this circuit to what you found for the half wave rectifier in exercise 3. So mean value which we have found out in the previous question. Now we will compare that to here. Okay, so this is the circuitry as we mentioned. Now let's go here. I have already made the circuitry, so can save the time. So yeah, 1 4. So this is the circuitry, same circuitry as given. We have made this, and we can see 1 mega ohm resistor and 1 microfarad capacitor, and this is the same signal. Let's run this now. Okay, this is running for the 10 seconds. Okay, so just click here and here, inputs and the outputs that we want. Okay, add plot plane and go here. Now just click on control, press this. We are getting the 409 millivolts. Okay, so this is the value which you are getting. Okay, and the range of the fluctuations, that is also something which you have to see. You can just click here. See, yeah. So 412, 411, 412, 412, 411. So what we have achieved, the range of the variations in the previous question, which when we changed the resistor to 1 mega ohm, was like pretty large, right? 20 millivolts was where we're changing. Now here this percent DC is changing very less, right? 411, 412. So if we consider the maximum range for it which is changing is, let's say it is changing for more than like 1.5 millivolts, right? So approximately with that much change is happening. So 20 millivolts to 2 millivolts, that is the change that we have achieved with this full wave rectifier. Okay, so this was the question. Okay, working on this, you already understand in the lecture that how it works. Basically for the positive clock cycles, the diagonal components will turn on. Okay, so for the positive cycles, this D2 and this D4 will turn on, and for negative cycle, this D3 and D5 will turn on. So where this resistor will be having the waveform all the times. Okay, so that was the characteristic of this. And now let's just move to the question number 5. Okay, so just basically go here. Basically this is the question number 5. Okay, so measure the IV curve of 5 mm dia standard LED to show that it is the diode, and what is the highest power of voltage applied for which LED remains dark. Okay, what is the lowest voltage at which you see some light from the LED. So in this particular question, we are going to find out the voltage drop across the diode. Okay, as I already mentioned, the diode will not take the run on immediately. Okay, so what it will do, it will have some voltage drop across it. So for the voltage drop for which the diode is already given positive voltage as the anode and negative in the cathode, it is still not on. Okay, so that voltage, that is known as forward bias voltage, that is the voltage drop across the diode we need to provide, and that is something we have to find out from this LED, from this question. Okay, so I already made the circuitry. You can just remove this here, question number 4. Yeah, so this is the circuitry. Same, what I am trying to do is that I am increasing these voltage value from 0 to 5 in terms of in steps of 0.01 volts. Okay, so you can have precision. Okay? 1K is the value of this resistor, and this is the LED. Okay, you can, how do you get this? Just click D, and then basically right click on this, pick new diode, and you can go here and you can click anything, right? Zener, Schottky, LED. Yeah, there are LEDs given. Okay, these are the different LEDs. I have picked the first one. Okay, you can pick as that as well. Okay, just remove this for now. This is the value, sweep value, and just click run. Okay, basically voltage drop across diode. This is the voltage drop across the diode, the current which is flowing from here, and this input voltage variation. Okay, add plot plane, add plot plane. Okay. So the first one is what, VN001, this is the input. VN002, this is the diode voltage drop across the diode, and this is the current. Okay, so what we are essentially going to find out is the value of current. Here you can see that it is what in terms of picoampere. Okay, and when it changes from picoampere to microampere. So this is pico, this is nano, and this is just now here it changed to micro. Okay, so approximately it is 0.5 volts. Okay, a 0.5 in this range, 0.5, 0.6 here. You can see that picking up, this current is picking up, this graph here from this nano, the pico, nano and micro, it is picking up, and then it is very going to this particular values. Okay, the input voltage, which is this, okay, here it is varying approximately. You can say that 0.5, 0.6 volts approximately are the voltages where this current is flowing. The current flowing means LED is not dark. Okay, for ranges of voltages which are below 0.5 or 0.6 for this particular case, the LED will be in dark. But when we have voltages, the input voltage is beyond 0.6 volts, the current will be in terms of microampere, LED lighting itself. Okay, so increase in the current will result in increase of the brightness. Okay, so increment in the current will result in increment of brightness. So you can see the LED will become brighter and brighter as we increase the voltage. Okay, that increase of voltage result in the increase of current, and increase of current will flow will result in the brightness. Okay, so that is the current here is the allocation of the brightness. So this is the fifth question. You answered all the question mentioned in the PDF itself. Okay, now let's just go to the next and the last question. So the last question, the sixth question, it is about Zener diode. You probably have studied about Zener diode in the lectures. What is the use of it? It is just used for the voltage regulation. Okay, and the use of it is in the reverse bias. Okay, so it no matter how much amount of the current changes across it, it makes sure that the voltage across it remains the constant value. Okay, this basically you can how to see the waveform across the Zener diode that you get. The voltage, what waveform what you will get is that you will get the constant value, right? So waveform in terms of that how the change in the voltage of the input does not affect the Zener. That is something we are going to learn from this question, and it is used for as a safety measure. Okay, this basically the value of this curve should have some quantity inputs like 7 to 10. I will show you in a bit that the ranges which are written here, you will not be able to see the actual characteristic of the Zener with these values. We will see in the LTspice. Okay, see the Zener diode which is considered here is approximately this it is having this voltage regulation across 5 volts, but the inbuilt Zener diodes which are there in the system in LTspice will not have this value. We need to find out this value, and we can use this value to check these voltage ranges, that whether it is giving the regulation or not. Okay. R2 is 1 kilo ohm. Okay, so this is the thing. Okay, so this particular question numerically you must have to do first, and then you can come here. Okay, the power dissipation is given as 1 volt. So with these values, let's say R2 is equals to 1 kilo ohms, that D1 giving the constant voltage of 5 volts here, 5.1 volts here, and the current which does not exceed 5 milliampere, then what can be the value of R1 in the range of this. Okay, so do this by using a numerical method. I think we already know about it. So right now we will focus on the diodes, Zener diode, which is given in the system in LTspice. See the characteristic of it. Okay, so let's just go to the circuit. Okay, so now just remove this 5th question. No. Okay, so yeah, so this is the question. The R1, R2, I am taking them as 10 kilo ohms. You can take it as 1 kilo ohm as well. Okay, this is the Zener diode which I am using. This is the model name, and you can see I am using this voltage values up to 0 to 200. Why am I using this is the reason. Okay, there is a reason behind this. Just right click on this, pick new diode, and go to Zeners. Okay, you can see this is the different Zeners given. This manufacturing company is onsemi. Okay, breakdown voltages are given 51, 60, 82, 100, 68. See what this breakdown voltage means. This is the voltage at which the Zener diode will come into action. Okay, it will make sure that the voltage across it remains this much. Okay, there will be a slight increase when the voltage, the 51 to let's say 55, 56, 57, not more than that. Okay, so of course the diode which is mentioned, Zener diode which is mentioned in the PDF, which is not present in my system, you can use that. You can download the model, you can use that, but for right now I am just using this onsemi diode 1N5369B, okay, which has 51 volt breakdown voltage. Okay, just click on OK. Okay, now variation of this voltage from 0 to 200 in the steps of 0.01. Just run this. Okay, so just click here at the input. What is the input? 0 to 200 volts, and what I am getting as output, just click here. This is the thing which Zener diode has, which none of the other thing will have. Okay, so you can see from here the input volt, the variation of the value of the input voltage is 0 to 200. See, this is the same curve as this. Basically what we are doing is that 0 to 200 variation, which is input voltage. This Zener diode is approximately giving me the constant value. Okay, just click on here and see, for ranges of voltages, let's say, which is from 100 volts to 200 volts. Okay, you can see this horizontal and this vertical. So you can see, sorry, click once again here. So basically you can just, okay, this is the click here, and you can see the for 100 voltage it is giving me 47 volts. Okay, now I am increasing the 100, 100, 200, 300, 4, and you can see the voltages are not changing in proportion to input. Here from 0 volts, see this, the range of voltages, of course there is some drop, but the voltage across this Zener was approximately half of the input. Okay, you can see 3.97, 1.98, and then it goes up to this particular point. When it becomes 100, and then on it increases approximately very basically it increases, but it is very small variation. You can see, right, 130, and approximately up to 200 volts it is just becoming 50 volts and not beyond that. So this Zener diode is giving the constant voltage after the range, after some range, 110 and so on. Okay, so this is the use of it. So for example, what is the particular use of it? Consider this load as sensitive. Okay, ranges of voltages is 50 or 100 volts, so you might feel that it is very large, but you can bring down the order, let's say 5 volts. Okay, here it is giving a constant voltages across this load. Consider this as a sensitive load. Okay, it cannot have higher voltage than 50 across this. Right now it is resistor, but if there is some sensitive load, you will not be able to have more voltage here. If it is more voltage, then this load might get damaged. Okay, so this diode will be used across it. What it will do, excessive current which is there from which must pass from this circuit, because see, this is the input voltage, it is increasing from 100 to 200 volts. 100 volt increments must result in a higher current, double current than 0 to 100, right? Because we have added 100 voltages. That current must not pass through this R2. If it passes through this, it will damage. So what it will do, it will make sure that across this resistor voltage is constant. Because of the constant voltage, the current which is flowing from R2 becomes constant. So the increase of the current will be taken care of by this Zener diode. Okay, which you can see the current here also, right? You can click here. Okay, see, up to this you can now just remove this, and you can just click here up to this particular voltages here. So approximately to this diode has 0 current. Now it is so 0 current in approximately so in nanoampere. Now it current starts increasing. See, it goes to milliampere and micro to milli, very fast, nano, micro, milli. Okay. So what happened, the diode incorporated and it took all the current that was excessive, which must not pass to the load, into itself, and made sure that the current made sure that the voltage across the load remains constant. So this is how you use a Zener diode to make sure that the load is safe. Okay, or the voltage accuracy you want to have, then you can use this diode. Okay, main thing is we had used this in the reverse bias characteristic. Okay, forward bias, we do not use Zener diode in the forward bias, we use it in the reverse bias. Okay, so this is how we particularly use it. Okay, so that was a lab. If you find value in this video, then like, share, subscribe to my YouTube channel, write down your thoughts into comment section. I will meet you in the next one. Happy learning.
Tell me pretty lies, look me in the face, tell me that you love me, even if it's fake.